Okay, so how many of you are concerned about your quiz grade? Just two? That's it? I figured at least 80 or 90% of the class. You all are confident you did a good job. Nobody likes a do-over. Nobody wants a do-over. Yeah, there was, so let me back up. So when I teach Thevenin and Norton, I usually like to use the phrase as seen by. And I pointed that out in, let's see, when we did, let's see, for one here. So right here, this is the example circuit that I typically use. Again, could be any circuit anywhere, could have any number of components, any number of sources, does not really matter. But typically, the analysis terminals, in examples, the analysis terminals may be given to you, okay? But when you're an engineer, you're working with a circuit, you're trying to find a Thevenin Norton equivalent as part of a, that's as relates to a component, then the phrase as seen by, or from the perspective of, or the load, they're all equivalent phrases. That's the kind of phrase that would be used. So for example, in this class, we'd work with models for diodes and for transistors, where you'd have like 3 or 4 resistors perhaps connected to a transistor. And you need to be able to find the Thevenin resistance as seen from the perspective of the transistor or as seen by the transistor. Then the transistor is removed and you analyze the rest of the circuit without the transistor to find Thevenin resistance. And so the reason I keep harping, well, keep stressing or emphasizing Thevenin Norton is because, in general, as an electrical engineer, you would use that technique a lot. And also, as pertains to this class, also we will see that technique. Okay. So in general, as an EE, you should be very familiar with this technique because you'll be using it often. It's one of the fundamental fundamental theorems of electrical engineering. Now, having said that, it is not a new analysis technique. It's not an analysis technique per se, right? They refer to it as analysis technique, but it's not an analysis technique. You learn about Ohm's law, KVL, KCL, node voltage, mesh current analysis, superposition, all of those techniques. For Thevenin and Norton, all we do is we take the circuit and we analyze it based on the requirement of the component, meaning you set up that circuit. If you take this as an example, I ask you to find the Thevenin voltage as seen by resistor R6. Then you remove R6, right, as I have here. And then you analyze this circuit between those terminals that are left behind. When you remove R6 from your analysis, these pair of terminals are now open. So you analyze this circuit, you determine the voltage at those terminals, and that is your Thevenin voltage. And that was the point of that question. Okay, that was the point of the question. How do you find the Thevenin voltage as seen from the perspective of the current source, the voltage source, and the resistor? So you remove that specific component from there, and you analyze the circuit for Thevenin voltage. Then you analyze the same circuit for Norton current, and you analyze the same circuit for Thevenin resistance. And the analysis that follows after that first step, well, you already know how to do that. I have confidence in you. I have confidence that you know how to set it up too, but I think there's a communication gap between what I use and what the students would have learned. And so in the first section, there was even more confusion. All the hands went up. So I'm surprised that very few hands went up here. So now, how many of you would like a duo? Not many. I'm still surprised. But does this make sense? Does the question make sense now? Did it make sense while you were taking the quiz? Okay. Yes. Yes. So the question being asked is, Thevenin resistance as seen by I1, then we remove I1 from our analysis. Let me draw it out here. So the circuit would look something like this. You'd have a voltage source, resistance, resistance. This would be left open because it's from the perspective of I1. R6 would still be part of the circuit. And these are your terminals of analysis. Now in the lab, here, of course, you analyze this to find VTH. In a lab, if you want to measure voltage, you determine your terminals, you take a multimeter, connect it to those terminals. 10 seconds, measurement is done. Doesn't take long. The actual calculation for Thevenin Norton takes much, much, much more time than the actual measurement in the lab. Okay. For the current, is the same thing. If this is VOC, all we do for current is we place a short between the two and you measure that current. In the lab, again, you don't have to make any changes. You don't have to make a short because a multimeter itself will provide you the short circuit. So you keep the multimeter connected, switch the mode from voltage to current, automatically measures the voltage first, then it measures the current. Thevenin resistance, exactly the same thing, but for Thevenin resistance, you have to reduce all independent sources to 0. All independent sources to 0, meaning you replace the voltage source with a short circuit and you replace the current source with an open circuit, right? And so you'd have to do that 3 times on the quiz. Once for the voltage source, one for the current source, another time for the resistor. So 3 times 3, 9 circuit diagrams. That's what I was stating earlier. How many of you had 9 circuit diagrams on there? Okay, that's good. You all know your stuff. That's good. Okay, any other questions? Any questions regarding anything you have done so far? Yes. No, sorry. It's I. My chicken scratch. I am. Yeah, anytime if you can't read, sometimes my handwriting is worse than a doctor's prescription. So, and then of course, the reason why we need to be able to find all 3 quantities is because if you have dependent sources, well, the first reason is, of course, if you have 3 quantities related by Ohm's law, you only need 2 to find the third, right? But if any one of those 2 quantities is incorrect, then your third answer will also be incorrect. So you'd end up with 2 wrong answers out of 3. So you always want to find all 3 of them to verify your answers. And then the other reason is, of course, if you want to find Thevenin resistance, it's easy. You just find Req. Sometimes all circuits we are not able to reduce all circuits to a single resistance to find Req. Or we may have dependent sources in the circuit like this one, which cannot be reduced to 0. So in those instances, we would need to find Thevenin voltage, Norton current, apply Ohm's law, or we can do as shown here, connect a voltage source at the output terminals, find the total current supplied by the voltage source, and apply Ohm's law that way. Make sense? Ring a bell from 113. Anyone, any questions? Yes. It is important. At the beginning, so the question being asked is about the polarity for when we make the assumption about Thevenin voltage. Well, you can make an assumption, right? So here we are given the polarity, so we don't assume anything. But if nothing is given, we assume the polarity. And we base those assumptions based on certain logic. Meaning if the power supply is connected to the plus here, we know current is coming this way, right? So then we would avoid choosing minus at the top because it doesn't make logical sense. So you make any assumptions, but it does not mean that at the end your answer would be positive or negative. If you get a negative answer, all it means is that the polarity we chose is opposite of what we actually calculate. That's all it means. So I guess the answer to your question would be it's not important. You can assume anything you want. But at the end, of course, once you find your answer, you have to change the polarity. All right. Any other questions? Okay. In section 1, we went all the way to like 858, 848, sorry. So there's a lot of discussions and questions over there. All right, let's start chapter 2. Solid state electronics, the foundation of everything that we're going to use for electronic devices. Okay. So electrically speaking, or electronically speaking, we broadly classify materials or everyday materials into 3 categories. One is conductor, the other is insulator, and the third is semiconductors, right? 3 broad classifications. Now, all materials have several different material properties, and material properties are highly dependent on their physical surroundings, namely temperature, pressure, humidity, to say a few, to name a few. Okay. So all material in everyday life, in this planet, has material properties, several different kinds of material properties, and all of those properties are highly dependent on our physical environment. When it comes to electronics and electronic devices, we are using specific materials, and we have a broad classification of conductors, insulators, and semiconductors. And the material property that we are interested in is resistivity. Resistivity is highly dependent on temperature. The reason I'm bringing this out right at the beginning is for the rest of the course, pretty much any course you take, and we talk about a device, we are always referring to room temperature. And room temperature can be broadly classified as 25 to 27 degrees C. Okay. Typically, it's like 27 degrees C because we use 300 Kelvin. And 300 Kelvin is 27 degrees C. So, generally speaking, every electronic device, every circuit that you analyze is always at room temperature. We never, unless explicitly stated that you are working at absolute zero or like in hot environment or a cold environment, it's always room temperature. So all the properties or the numbers that we will refer to will always be referred to as room temperature numbers. Okay. Resistivity is a material property. It's noted by the Greek lowercase letter rho, RHO, and units of ohm times centimeter, ohm centimeter. Actually, it's ohm meter, but along the way, they just use centimeters. And so it's just stuck. Pretty much every book, every author uses ohm centimeter. And equation for resistance, hopefully again you remember this, is rho L over A. Resistance is not a material property, right? Say, create resistance using resistivity. If you have a piece of wire or a piece of material, the cross section and the length cross section and the length can be calculated or can be designed to create a specific resistance. Okay, rho L over A. Did I teach this in physics or in 113, perhaps? In physics? Okay, yeah. But again, physics was a long time ago, right? Anyway, so resistivity again is a material property, and then we can use the equation R as rho L over A to determine or design our resistors of specific value. Okay. All right. So broad classification based on the numbers of resistivity. For conductors, rho is typically less than 10 raised to minus 3. For insulators, it is greater than 10 raised to 5. And then our materials of interest, semiconductors, are somewhere in the middle. So it's the entire range from 10 raised to minus 3 to 10 raised to 5. Okay. Now, because semiconductors have a very wide range, and depending on the element, of course, um, one of the key things that allows us to use them as either an insulator or a conductor is that we can introduce other elements into our semiconductor material. We can create either insulators or we can create conductors. Okay, so having a wide range of resistivity means that the semiconductors can perform as a insulator or they can perform as a conductor, hence the name semiconductors. And the reason why we don't call them semi-insulators is because we primarily use these materials for conduction, not for insulating or resistance. Okay, we use them for conduction of charge, conduction of electrons, conduction of electrical energy, hence semiconductors. And this table right here from the center of the periodic table lists the most common ones. Right in the middle are the two most important ones, silicon and germanium. Germanium was actually the first semiconductor material. The first transistor was based on germanium. And silicon very quickly took over or overtook. Two reasons why. Silicon is the second most abundant element on this planet, right? So it's very widely available. And then early on, research was conducted into silicon material. When you create semiconductor devices, you need material with the highest purity possible. You're talking about like 99.99999 long 9%. Okay. So out of millions and billions of atoms in a single piece of material, you'd have impurity levels, meaning external material would be very few parts per billions of atoms. Okay, that high level of purity. So a lot of research was done early on into creating a very high purity material using silicon and germanium. And once they discovered a method that allowed it to be mass produced, well, that's when it just took off. Okay, and then silicon became the de facto choice of semiconductor material worldwide. So here is basically column 4. Column 4 basically has 4 atoms in its outermost orbit, and that's where silicon and germanium shine. Carbon, however, even though it belongs to column 4 of the periodic table, has 4 electrons in its outermost shell, is not a semiconductor. It is actually an insulator. And there is a reason why, and we will see that just in a couple of slides when we talk about energy band gap. But carbon, again, is in column 4, but it is not a semiconductor. And then there are compound semiconductors where you combine elements from different parts of the periodic table to create a semiconductor. So for instance, you combine column 3 and column 5, you get a semiconductor. So aluminum combined with phosphorus gives you aluminum phosphide. There is gallium phosphide, gallium nitride, gallium arsenide, which actually is in the earliest LEDs, right? You create a compound semiconductor using gallium arsenide, you get LEDs because the energy is now dissipated in the form of light. Photons are dissipated. Then you might have heard of silicon carbide, perhaps. And let's see, gallium nitride, which is a big deal nowadays. They've been using gallium nitride in creating these fast charging devices. So you heard gallium nitride chargers. Again, it's based because the elements used in those chargers or charging circuits are based on the semiconductor gallium nitride. Okay. Let's see. This is where kind of stop for section 1. So I'm here for section 2 also. I'm going to stop class here today or end class here today. And we'll pick up here again on Wednesday. If you have any questions, let's talk outside or go back to my office. We can talk. I'll clear up the space for the next class.